Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. In our previous lesson, we talked about using semicircles as cross-sections to find the volume of a solid, and today we're going to look at triangles. Now, yesterday's or the previous video was rather short because we really only needed to do one example. Today we're actually going to have to do 3 different examples to cover all the sorts of different triangular cross-sections you could see. So let's jump down here to the page where we first start talking about triangles. We now have one more type of cross-section to talk about, and it's the most complex. We are going to look at triangles. What makes them complex is that we can use isosceles, equilateral. Actually going to have triangles here, so the grammar makes sense. Isosceles triangles, equilateral triangles, and any of the sides can be the one line in the xy plane. The first example we're going to do is actually the easiest. It's when we're using isosceles right triangles, where one of the legs lies in the xy plane. So let's go ahead and take a look at that one before we get into some more of the difficult examples. You'll notice we're using the same function from the previous lesson, as well as the first part of this one. Now, we are doing isosceles right triangles, which, if we just sketch one of those on paper, it's going to look like this, right? Both the legs are going to be congruent. We're going to have a right angle. If one of the legs is in the xy plane, well, all of a sudden our triangles are going to look like this. So the hypotenuse is going to be the one that's not face down. And we're going to get a solid, kind of starts looking like this. Because they're isosceles, right, we know that these sides are going to be the same. They're going to be congruent. So that's going to make it a little bit easier for us when we're figuring out our formula to use. As always, I want to find the volume formula for one of these cross-sections and then just integrate over the entire interval. Well, the volume for a triangular prism, because that's what these cross-sections are, volume would be the area of the base, which in this case is 1/2 base times height, times the distance between the bases, or the height of the prism. So we'll call this H1, we'll call this H1 and H2, where H1 will be the height, and H2 will be the distance between those bases. And B will just be this distance right here. Okay, let's sketch one of these, of course, on our other graph. Right, we need to figure out what B is here. Well, that's the distance between the red and the blue curve. So let's make some substitutions there. We're going to get volume is equal to 1/2. B is going to be 6 minus 4 times the natural log of quantity 3 minus x. That's B. H1 is the same as B. Right, they're the same because these are isosceles right triangles. So we can just square this, and all of a sudden this becomes, this becomes B times H. Now we still need our H2, but that's just our dx. Right, that is the distance between the bases. We want that as small as possible because we want to fit as many of these cross-sections into our solid as possible. I have my formula. I am ready to set up my integral. Right, this was just the volume of 1. I want the volume of the whole solid. So it's going to be the volume of the integral over 0 to 2 of this quantity. I am not going to be able to distribute that 1/2 because we're squaring what's inside of my brackets. So I'm just going to have to leave everything as is. Again, this would not be an integral you're doing by hand. You would evaluate it with your calculator. And that's what you should do. Pause the video, figure out what the area of this solid ends up being. Turns out it's approximately 13.133. So as you can see, pretty straightforward when it's an isosceles right triangle where one of the legs is flat down, right? One of the legs is in the XY plane. We're now going to look at two examples where that's not the case. And you're going to see coming up with this formula just becomes a bit more difficult. Let's first look at an example where we're actually going a little out of order here, where we have an isosceles right triangle, but it's the hypotenuse in the base, or as our base. So let's look at this example right here. And this is actually a multiple choice question, so all we have to do is figure out how to set up our integral. Although it is one of those tricky ones where it says E is none of the above, so you really have to know what you're doing to get a question like this correct. Okay, first thing to take note of is the type of cross-section we're using. An isosceles right triangle with the hypotenuse in the base. And it's going to be perpendicular to the x-axis. That's nice. That's a more familiar integral for us where we write everything in terms of x. Now, we still have an isosceles right triangle, but when we start to draw these, I'm not going to go through an entire picture here, but this is going to be the right angle. That's going to be the right angle at the top. So if I draw this over here, here's our right angle. Our hypotenuse is the one the side that's face down, and these two sides are the congruent ones. So our formula for the volume of one of these cross sections is going to be the area of the triangle times the distance between the bases, right? That would be our little dx. So we know what the width is going to be, or the distance between the bases. That's going to be our dx. So we just need to focus on the area of this triangle. Well, the area for a triangle, that formula doesn't change, right? We have area equals 1/2 base times height. And for this orange triangle, the base is actually a pretty easy dimension to figure out, right? That is just going to be the distance between our red function f and our g function blue. So as I start to build out this area formula, I get area is equal to 1/2 times the difference of f of x and g of x. Now I just need to figure out what the height is, right? That's the trickier part to figure out here, but it's actually not too difficult. If I draw in an altitude, which would be my height, I create, again, two more right angles down here. And what has actually happened is I've split this orange triangle into two congruent triangles. You could prove that they're congruent by hypotenuse leg congruence. If I just look at, if I make it obvious here, I've got a pink triangle and a purple triangle. We're bringing us back to geometry. But those are both right triangles. By the reflexive property, these legs are congruent because they're the same segment for both triangles. I actually put two tick marks there. And the hypotenuses of both triangles are congruent. So by HL, these triangles are congruent. Now, again, another theorem, CPCTC, right? We would then know, because we have congruent triangles, their corresponding other sides will be congruent as well. So this base is really being split into two congruent pieces. Okay, here comes the fun part here. Now let's do this in black. We can actually show that these two sides right here are congruent. And that's because both of these triangles, not only are they right triangles, they are 45, 45, 90, just like the large orange triangle. That's a 9. They're not 45, 49. They're 45, 45. Turns out that if you have an isosceles right triangle, you draw an altitude from the right angle to the hypotenuse, you will create 2 additional 45, 45, 90 triangles that are congruent to one another. And again, that's because we know this angle was 45 to begin with. Well, we have our 90 angle in blue, so this angle up here has to be 45 as well. Which means this triangle is isosceles, and, oops. And this side is now congruent to this side, right? So we actually don't have to have 2 and 3 tick marks. We could just make those both 2. Long story short, right, we already know this length, right? That is just half of B, half of the entire base. Well, because that is the same as the height, that's also the height as well. The height is just going to be half of the base. So we actually need a little bit more space here. Let's do this over here. So our area is equal to 1/2 times the difference of F and G. That is our base. Our height is 1/2 of this. So times 1/2 the difference of F and G. You could do a little simplifying here. This ends up just being 1/4 times the difference of F and G squared. If I wanted to find the volume of one of these cross sections, right, it would be the area times our little dx. So the volume of a cross section is going to be 1/4 times the difference of f and g of x squared times dx. And of course, if I want to find the volume of the entire solid, I'm just going to integrate over the interval 0 to c. Right? They give us this intersection point, the x value c. So 0 to c of all of this. And you could also move the 1/4 outside the integral using integral properties, but we'll just leave that like that for now. All right, let's go see if that matches an answer. Got a lot going on the screen here, but that does match the answer D. Very close to A, except A has 1/2 rather than 1/4. Okay, so actually this one wasn't too bad. A little bit more complicated than when it's one of the legs lying in the xy plane. But based on properties of isosceles right triangles, it's not too difficult to figure out the height when it's the hypotenuse that's lying in the xy plane. That being said, I don't just want you to memorize the formula based on which side of the triangle is the one face down in the xy plane. If you forget, you can always go through this process up here, right? You can think about what an isosceles right triangle looks like. You can then use principles of geometry to figure out what the relationship is between the base and the height and how to figure out both. All right, one more example to do. This one is a bit more complicated. We are rising in level of difficulty. We're actually going to go back up here for this. All right, so for this one, it says the base of a solid S is the triangle enclosed by the line x plus y equals 1. Notice that that function is not solved for any of the variables, the x-axis and the y-axis. Cross sections are perpendicular to the x-axis and are equilateral triangles. So 60, 60, 60 as far as our angles are concerned. We need to determine the exact volume of S. So we are going to have to work out this integral by hand. We're not going to use a calculator. But more importantly than working it out is going to be the setup here. So our cross sections are perpendicular to the x-axis. So the base is going to be something that looks like this, right? And I'm not going to draw the whole thing, but it would be, right, something like this, where all of these angles are 60 degrees. So again, if we can find the area of this triangle, well, then we can multiply it by the infinitesimal width, right? If I try to draw this with perspective, it's probably going to go rather poorly. But it's something like that, right? Our width between those bases would be our dx. So we just need to focus on finding the area. I will just leave it like that. And in fact, I'm going to draw it over here. "60, 60, 60. So notice that it doesn't matter which side is the one lying in the xy plane, right? Because all the sides are going to be congruent because it's an equilateral, just like all the angles will be congruent. Let's start off with the formula for an equilateral triangle, for any triangle really, right? Area is equal to 1/2 base times height. Well, the base shouldn't be too hard to find, right? That is going to be the distance between this blue line and the x-axis. Because these cross sections are perpendicular to the x-axis, we're going to write our integral in terms of x, which means we want this function to be in terms of x. Right now, it's just a curve, x plus y equals 1. That's right as a function in terms of x. I'm just going to subtract x from both sides. So this ends up becoming y is equal to 1 minus x. That is going to be the length of our base. So I can start off with area is equal to 1/2 times the difference of 1 and x, 1 minus x. Well, I still need to figure out the height of this triangle, and that's where the challenge comes in. Let's draw an altitude in there for the height. So now let's just look at 1/2 of the entire triangle here. I'm going to outline it in light blue. We've now created a 30, 60, 90 triangle. 30, 60, 90. And just like when we drew the altitude for the isosceles right triangle, we have created two congruent triangles here. So I'm not going to go through all of the steps for why they're congruent. I think you could think through that on your own. We did it for the above example. But it turns out that both of these sides will end up being congruent, which means if we know the whole thing is 1 minus x, so we know that half of it is 1/2 times the difference of 1 and x. So now we just need to figure out what this height is going to be. And we could use trig, right? We could use sine or cosine, but we should know some relationships about 30, 60, 90 triangles. And then we won't have to have a sine, a cosine, a tangent in our integral. Well, I know that in a 30, 60, 90 triangle, let me just sketch another one over here. If I know what the shortest side is, well, the hypotenuse is going to be 2 times that length. The middle side or the side across from the 60-degree angle, right, the second longest side, is going to be root 3 times the shorter side. Okay, so that's the relationship. If you know the shortest side, multiply it by 2 to get the hypotenuse. If you know the shortest side, multiply it by root 3 to get the side across from the 60-degree angle, or the second longest side. So that's all I have to do up here. I need to multiply this product right here by the square root of 3. That's going to give me the area of that black triangle. I can do a little simplifying here. Area is going to be equal to root 3 over 4 times the difference of 1 and x squared. So now if I want to write a volume equation for just a single cross-section, so the volume of 1, right, well, that's going to be equal to the square root of 3 over 4 times the difference of 1 and x squared times our dx. Right, that is going to be the distance between the two bases. If I want the volume of the entire solid, right, if I want to sum all of those cross sections together, well, I'm going to have to integrate over the interval 0 to 1 of my volume equation or volume function. Now, it looks like it might be tough to evaluate this by hand, which is what we are going to do here. I don't know if they'd give you one with this much algebra on the AP exam. I tend to think not, but it is possible to do it by hand, so we will, and it comes out fairly nice. What we need to do, though, would be to square that binomial, and then just use the reverse product rules, or the reverse product rule. So what I'm going to do is I'm going to erase everything over here. So you can pause the video now if you need to think about something a little more before we move forward, but I'm going to use this space for our integration process. I may need 2 columns, who knows? Okay, so I could pull that coefficient outside, right, outside the integral. So I'm going to get the square root of 3 over 4 times the integral from 0 to 1, and then I'm going to actually square this. So I'm going to get 1 minus 2x plus x squared dx. Let's go ahead and take the antiderivative. I'm going to get x minus x squared plus 1/3 x cubed. Evaluate from 0 to 1. That's going to give me the square root of 3 times 4. If I substitute 1 in there, I get 1 minus 1 plus 1/3. Let's put that in parentheses. Minus everything evaluated at 0, which just ends up being 0. So I get the square root of 3 over 4 times, well, 1 minus 1 is 0, plus 1/3 is 1/3, which gives me square root of 3 over 12. So I guess I take it back. There's not too many algebraic steps here. So this could certainly fall into it would fall into the non-calculator portion if they decided to put it on the exam. Okay, that is going to do it. We have covered the 3 types of examples you could see with cross sections that are triangles. I know we didn't cover where the cross sections are perpendicular to the y-axis, but the process would be the same, right? Our integral would just be in terms of y rather than x. The same concept, the same idea is there. As always, enjoy the rest of your day, and we will look forward to seeing you next time.